Yeah, so it's important I say David's name loud. He's sitting right there, so feel free to talk to him. David Clausen and Shang Tang at St. Louis, and also with former student Jiawei Zhou, who's currently a postdoc in Beijing. Okay, so the study for this is symplectic manifolds. Actually, it could be more general. It could be pre-symplectic. It could be also, I think, multi-symplectic, as Edra was talking about. But we only required for most of this talk just the distinguished geometric structure that we're caring about is closed form. Okay, and the main goal, of course, for in a setting of manifolds, you have a geometrical structure. You want to find invariants that can depend on the geometric structure that you have at hand, right? Now, typically, we're very familiar with the complex case. In the complex case, in the case of maybe MJ, where this is an integrable complex structure, then the complex structure allows us to, use special coordinates, right? Just work with holomorphic, anti-holomorphic coordinates, right? And in fact, right, so in the smooth case, we have the standard DGA, the RAM DGA. The complex case, instead of working with the RAM forms, you could work with PQ forms. And, the differential decomposes to del and del bar, right? And you have a natural Dobleau DGA that you can work with, right? Now, the case where in the case where we have the geometric structure is a form, right? You can ask the same question: is there a nice DGA we can write down that sort of encapsulate a lot of the invariants that maybe at least the basic invariants that we're interested in, right? And so that goes to the word here, cone. So I like to point out the mapping cone algebra that I think is useful to study. Consider whenever you have a geometrical structure that is a closed form. Okay, so it turns out this is also in general a DGA, right? So in our case, depends on M and omega, and there's a differential that squares to 0, and there's also a natural product on this space. Okay, I'll just write the product as X. Okay, so exactly what is the mapping cone? Well, we have omega is a form, right? It's sitting in the Durham algebra. And what can we do with the form? Well, we can, of course, take its differential, but that gives 0. That's not so useful. But in addition, we can wedge it, right? Do the exterior product, wedge it with omega per se. So in an algebra, usually we have a differential. We want to have d of something, right? So you consider, at least I could take the d. This is still something we have. This is just in the Durham case. But in addition, we have a form that we can wedge with. Maybe we wedge with this guy by omega, wedge up to omega, right? We can have with this k plus 1, right? Mapping k minus 1 to k plus 1. Okay. Now, if I were to write this in terms of a vector, what we have here is effectively right? So a pair of forms of degrees, right? So let me write it in vector notation. K minus 1, right? Okay. And we would like to algebra have a differential. Differential, if you want to try to make it simple, you want this differential to be a linear type object. So maybe I want to have a linear matrix here. And okay, so in this case, I have this k go to k plus 1. That goes into D, right? K minus 1 by wedging. I have this guy here, omega wedge, right? Seems natural. And okay, I want to fill up this matrix, right? And probably easiest to do a triangular one. Let me put a 0 here. And then, this one down here, maybe I could also do a D here. Okay, I do a D. And with the right sign, you get a nice differential. Okay, so this is exactly what I'll call the cone. So this guy here is my differential. I call DC. And this guy here is what I call cone of K and omega. Okay, so cone of K omega. Omega. Okay. Okay, so from this picture, our point of view is, you see what we're doing here is nothing more than we connecting these two guys together, right, as a vector. You know, it's a case of forms, right, two sets, and they map to this pair here, right? And we have this combination, right? So you want to check. Okay, so there's a nice grading here, right? The grading, if you like, just follow the top one. You want to check that this DC squared to 0, and this is easy to do. But if you're seeing this for the first time, maybe just take a quick look. Just takes a second, so I still think it's worthwhile to write it down, right? So certainly here, this part here is first term square to d squared. The 0 on the bottom. In the off diagonal one, you get d omega plus d omega minus omega d, which cancels by Leibniz rule, right? Just move d across, right? Omega is a true form, right? So this cancel, and the bottom is also d squared, right? So this evidently gives you 0, right? And then you could ask the question, okay, we have the cone, we have a differential that squares to 0. How about the product, right? How do we get the product? Well, the product, right? So our cone consists of this omega k, right? And omega k minus 1. Okay. Now, these have different degrees. Let me insert a formal parameter, right? Let me insert a formal, this guy's formal. Data is an element of, in this case, I need a 1 form to make the degrees match up, such that the data is equal to omega. Okay. So I want to change this and write this as a formal 1 form, right? And why do I do that? Because if now I look at DC acting on cone of K, right? This DC is this guy, right? But this is nothing more than just a standard exterior derivative of this omega k plus theta wedge omega k minus 1, right? So you see the first d just acts on omega k, right? The wedging of omega just comes from d acting on theta, and the last part you get the minus sign traveling through to act on the last omega k minus 1. Okay, so basically this becomes just a regular Durand form, and then we know the Durand form has a wedge product, and that's the product that we have. In this case, theta wedge theta is equal to 0, right? So we always have one single theta. Okay. And so this gives us a nice mapping cone algebra, right? That's a DGA. Okay. And that should be nice, and because once we have a DGA, in some sense it's very similar to Durand, right? Just basically 2 sets of Durand forms, right? You can do a lot with it, right? So you think that you can do much with it? Yeah, question?
Yeah. So it looks obviously as forms on a cylinder. So how we can see the difference between cone and the cylinder here?
Yeah. So the notion of mapping cone is usually, right, that people consider mapping cone topologically as a map of function from a space to a y, right? And then you, as you say, a cylinder, right? So you could take, so if let me draw x here, and it maps, let's say, to a y space, right? And usually you draw a cylinder, right, to the f of x, right? It becomes a cone if you shrink this point to like this. So basically you identify the space, right? So in mapping cone, sometimes it's also sort of as a quotient, right? You're taking basically the cone is roughly speaking, right? You're taking y f of x, right? Because you're identifying into a point.
Right. And so how can see it algebraically? So your theta is like dt.
Yeah. So here there are 2 sets of closed solutions, right? One is that it's right. So if I right. So if I just write, let me write the ck as a cone, right? Let me say consists of just write it plus data. So data in some sense is sort of the generator for this set, for the bottom one, right? So if you have this, what is the condition? The condition is you get this relation equal to 0, and also b equals z equal to 0. Okay, so you see that it consists of, if it has itself is closed, it's a closed form, or now the z needs to be close, right? But a z wedge omega could be exact, right? So in cohomology, if it's exact, it's sufficient, right? Is that clear? Okay. All right. Any other questions? Okay. All right. So, okay. So we have an algebra, and probably the first thing you want to know is, okay, we have an algebra that should give us some cohomology. And so what is this cohomology? What is this cohomology? Right. So the cohomology of this cone. And does it really depend on omega? Right. So you might ask this question. And it turns out the cohomology can be calculated. I won't calculate it for you. It comes from an exact sequence, gives the long exact sequence. It consists of basically the following. The co-kernel of, you look at the omega map from hk minus 2 hk plus the kernel hk minus 1 to hk plus 1. Okay. And this should remind you that we know that in de Rham cohomology is actually a de Rham ring. So we have certainly the, if I take k, the natural product on the ring, hk plus l, right? And what we're doing basically is we set this guy to be omega, the first one to omega. This gives a map to from L to h L plus 2. And certainly this is a linear map on, if I take this as a class, and we're basically looking at a linear map that's called kernel and kernel. All right. Now, if you're in Kähler manifold, this linear map, the kernel and co-kernel are fixed. But in general symplectic manifolds or other type of manifolds, this linear map can change as omega varies. Okay. And in fact, this cohomology was previously recognized in a different way. This is work about 10 years ago with STL and Zongjing Cai, that this is related to a type of complex that you could write directly in the symplectic, on the symplectic manifolds without using this additional cone structure. Okay, we call it a primitive complex. And this is work with Cai and Yao. Yeah. And this equivalence with the cone was some work from about 4 or 5 years ago with Hiro Tanaka. And we equate it with the cone. Okay. All right, but I want to emphasize today, well, in the last 10 minutes, once you have a DGA, there's, it's very similar to de Rham. De Rham has many different representation of the same algebra. And so here you could do the same. You can represent this cone in many different ways, and you get a lot of interesting results. Okay. And so let me give you two examples of them. The first one is work with David and Sheng on what we would like to call symplectic Morse theory. Right. So recall Morse theory is the notion that we want to get basic invariance of the manifold, right? Global invariance, right? The functions are global invariants, and we could try to get those global invariants from the functions. But you have to look for special functions, and you have to look for Morse functions. And Morse functions are special in the sense that the critical points, so P is critical, right, are non-degenerates, which means that you have a non-degeneracy. In some sense, at P, this is non-zero determinant. Because it's non-degenerate, the Hessian matrix has non-zero eigenvalues. So you could, they're either some combination of positive eigenvalues and negative eigenvalues. And if you count the number of negative eigenvalues, we call that the index of the critical point P. Okay, so that's called the index of P. It's the number of negative eigenvalues of the negative eigenvalues. Okay, now right, so you probably know that the Betti number can be could be estimated by basically looking at the number of critical points of certain index, right? But moreover, we have a Morse complex that's dual to the Durand complex, right? So recall the Durand complex, we start with omega k. The Morse complex, right, starts with as objects, let me call it CK. These are just our module generated by index k critical points, right? Index k critical points generated by, okay? And okay, so in the Morse complex involves more than just the manifold. Of course, we have to introduce a Morse function, which we'll assume to be Morse spell just for simplicity, and also a metric G, right? The differential D on the Durand corresponds to gradient flow, right, on the between critical points, right? So the gradient flow, nothing more than just, right? So you do need a G here, dt, dj, ddx of f, right? So just the gradient, but with respect to a metric. And key of here is that the Durand, you get the kernel over the image, and then so we can write the Morse as also the kernel over the image, right? Now notice that this guy is dependent on both, right? By construction, dependent on the Morse function and the metric. But what's really neat about this is that we do actually get an isomorphism. Okay. Now we can do the same thing, right? So now for this cone cohomology, for the cone cohomology, right? So what do we have, right? So the cone case, right? So on the, let's say just the cone cohomology, we start with the cone. The cone is cone forms are just in some sense a linear combination, right? Well, it's just two sets of forms, right? Now, if you look at this chart here, right, associating the CKs with omega k, so you could just repeat it here on this side, right? CK plus CK minus 1. Okay, so the interesting here is if we have a Morse type theory here, we involve both two pairs of critical points possibly at the same time. All right, so here we have DC for the differential, d wedge omega minus d0. Okay, now if I were to consider a differential on this space here, well, some natural guesses, you should hope that the 0 should still be a 0. The D should still be a L. Okay. The key part here is what is the omega wedge that contains basically information we want, right? So this is the information of the symplectic structure, right? What is the omega wedge? Okay, so we want this omega to somehow live, right? So this deltas are gradient flows between critical points, right? So we're living in the language of critical points, gradient flows. How can we bring in an omega into the story, right? Okay, so it turns out there's a natural object you can define. This was actually defined back in the 1990s by study by Austin Brem and Vertebo. So C omega acting on, let's say, a K index critical point. Well, you can consider sort of all the flows. So this we know we have to map to K plus 2 index, right? So K plus 2 index, right? So you consider all the flows from this K plus 2 going down to index K, right? It's going to give you a moduli space. So this is integrating summing over K, pk. And let me take, so this actually becomes a submanifold of dimension 2. So once you have a submanifold dimension 2, we can integrate over. and that's it, right? So do you think you have differential form? What can I do? I can take the differential, I can integrate. Well, here we integrate, right? So, okay, so it turns out there is actually also a Leibniz type relation, which we proved very carefully in our paper with David and Sean. And then we get cone, right? So this is m omega. Now this part here with Morse of let me call it also cone, right? So now this part omega depends on f and g, right? So, right, because it's really based on a Morse function and flow, right? Okay, so are they equal? And so that's the theorem we were able to prove that our theorem that in fact this construction is equivalent. Okay, so with this you can also get you know the Morse inequalities, all things that you want to do with Morse. Okay, but let me go on to the next application. Again, David's here, so just ask him any questions. He's also graduating, I should say, so he'll be happy to answer all questions, I believe. Okay, so another topic of interest is the notion of we hear a lot of talks about bundles. So there's a natural notion of symplectic flat bundles that comes out of, or flat connections, I should say, that comes out of the story. Okay, and you might recall, so let me draw another chart, right? In the smooth case, smooth, right? The notion of flat connection is nothing more than f equal to 0, right? The connection such that the curvature is 0. And the reason for that, one of the interests, there's many interests, is that if we consider Durand forms that are twisted, right, that takes value on the bundle, right, and we want to consider the differential complex, right? In this case, we have to throw in a connection, right, to allow for the twisting on on taking values on the vector, right? And but if we want to get this to square to 0, right, because we want it to be a differential complex, right? This is exactly the curvature, right? So if we use a flat connection, we can actually twist the Durand complex, right? And in the case of complex geometry, right, the notion of a smooth of a flat connection is also used very importantly in many cases, right? So now in this case, the natural object to consider is a del bar operator, right? You're looking at basically the 0, 1 component of the connection, right? So naturally, the requirement is that the 0, 2 part is equal to 0. But this is basically equivalent to a holomorphic vector bundle. Okay, so this is nothing more than a holomorphic vector bundle, which is prevalent in everything complex people do, right? So now you could ask the same question, m omega, right? In symplectic case, do we have an equivalent notion of a flat connection? Okay, so now instead of what can we use? Well, we have this cone complex, right? We can use this cone complex and try to do the same thing, right? So now we're looking at this map from h omega k minus 1 to omega k plus 1 k, right? Okay, so I had this DC before. Now I want to also twist this by a 1 form, okay? But what kind of 1 form can we twist it by, right? Okay, so 1 form, right? So let me write it's a cone 1 form, right? So it should have a data part, right? So maybe it's just an ordinary 1 form on the base, a data part, and also let me write the function as b. Okay, so a and b, right? And so similar type of equation to a d plus a, we do want basically f, which is dc plus a squared equal to 0. Okay, so this turns out to be equivalent to the condition that f is plus omega b is equal to 0 and dA of b. Okay, so this is fa db equals 0. Okay, I still have 1 minute, I think, right? Yeah, okay, thanks. All right, so this turns out to be exactly our condition for symplectic flat. Okay, so I don't have much time, but let me just mention, if you throw in compatible metric in 2 dimensions, symplectic flat is nothing more than 2D YAMLs. Just becomes YAML system. And in 4 dimensions, symplectic flat is actually a subset of self-dual YAML connections. Okay, special subset. But I want to mention one other thing. Since we're an audience, people deal with a lot of functionals. It's interesting to consider functionals that come from symplectic flat. Right. So let me just end with this. Right. So usually in the smooth case, again, the flatness condition, we have f equal to 0. The nice functional that people consider. Okay, so a little out of it. The YAML functional, right? So in this case, you look at f squared of the volume. Right. So what is nice about this is the zeros of this functional is naturally flat connection, right? And now if you do the same, right, for the symplectic one, you can consider the symplectic flat condition here, right, which I wrote it down as 2 equations here, right? If I insist that I want to write down, let me call this the cone YAML functional, and let me integrate over m, right? So I want the 0 of this YAML functional to be exactly symplectic flat connections. And so you can easily do that. And you write this as omega b squared as dA of b squared. Okay. And in the physics language, if you like, this is there's a YAML part, there's a massive scalar part, and then there's some interaction between the scalar field and the YAML field. I'm sorry I went over. Okay. All right. Thank you.
Thank you for the nice talk. Are there any questions?
Thanks for the talk. So I'm actually wondering, can you do the equivariant theory for the symplectic Morse theory? Like equivariant Morse function?
All right. Yeah, we haven't done it yet, but I think it should be.
Do you have any idea? Like, I'm like especially curious about like, what would be a correspondence for the equivariant perfect Morse function in this case? What will that give you? I mean, because in the general case, whenever you have an equivariant perfect Morse function, you know the Poincare polynomial can be just computed by the Poincare polynomial at fixed points. So I don't know, like, how does that result?
Yeah, so even in this Morse part, we can also do similar thing. Yeah, so you should be able to carry over.
Oh,
yeah.
Thank you.
Yeah.
Any other questions? Maybe we have time for one more and we can continue during the break.
Yeah, I was just wondering, so you introduced that formal parameter in order to take the product.
Yeah.
Does that like disappear when you do the when you actually like take the product to 2 things?
Yeah, the data wedge data is equal to 0.
Okay,
so you only always keep up to 1 order. Yeah.
I see. Okay.
Yeah, 1 power of data. Yeah.
Cool. Thank you.
It's like a Grassmann there.
Thank you. So let's thank Li-Sheng again for the great talk.